So this tutorial is going to be on the study of thermochemistry. So we'll talk about some definitions and do a little introduction so you kind of know what you're in for. And then we will discuss this idea of enthalpy. And then we'll talk about heat exchange between system and surroundings. And then finally, we'll talk about how to draw enthalpy and energy diagrams. So some definitions. We need to talk about what energy is. So when we talk about energy in chemistry, we can talk about energy as a method to move an object or to do work on an object. So that would be like a combustion engine. The energy of a chemical reaction can be used to actually move a piston in an engine, and that creates, of course, work that makes your car go. We can also define energy or talk about how energy can be used to raise the temperature of an object or increase its heat. So there are a bunch of different kinds of energy. You have potential energy, kinetic energy, heat energy, light energy. And in this chapter, we're going to focus on heat. So that's the focus of this chapter. So heat is always transferred from something warmer to something cooler. And you need to know that heat is not the same as temperature. Temperature is actually a measurement of the kinetic energy of the particles of matter. So you can imagine that this, whatever piece of metal this was, the particles had a certain average speed or kinetic energy, and when you add heat or when they absorb that heat, those particles begin to move a little bit faster. And temperature is a measurement or a measure of that average kinetic energy of those particles. The unit on heat energy, heat's measured in a unit called joules. And joules are actually sort of the SI or the standard unit. We used to use calories. You've heard of a calorie, I'm sure, as the unit for heat, but we now use joules. So thermochemistry, which is what this chapter is on, is the branch of chemistry that's dedicated to changes of heat in reactions. So if you are someone who designs combustion engines, you'd be really interested in thermochemistry. Or if you're someone who determines the number of calories in a food, you would be studying or you would be interested in thermochemistry. So when you talk about thermochemistry, we need to define what the system and the surroundings are. So the system and the surroundings together make up the universe. The system is the part that you're actually going to focus on. So for example, in this picture of hot coffee, we define the system. So let's say we define the system as actually being the molecules of water and coffee that are in the cup. So that's your system. The surroundings are everything else. So the cup and the plate, and if your hand were touching this and all the air around it, and pretty much everything else in the universe, that's your surroundings. The same would be true with a combustion engine. So a combustion engine, we can define the system as the molecules of gas and oxygen that are in the chamber. And then the surroundings are everything else. The piston, this little rod, and that turns this, I don't even know what these things are called, sorry. But the engine itself would be the surroundings, whereas the molecules in the chemical reaction of combustion is your system. And in thermochemistry, we're studying the exchange of energy or the transfer of energy between the system and the surroundings. So either from the system to the surroundings or from the surrounding to the system. So in thermochemistry, we focus on something called enthalpy or enthalpy. So enthalpy or enthalpy, however you want to say it, its symbol is an H. And it is defined as the heat content of a system. Well, it's only possible to actually measure changes in enthalpy. So we're really going to focus on delta H. Do you remember that delta means change and H is enthalpy, so changes in enthalpy. So enthalpy changes really are just amount to how much energy is absorbed or released by a system when it goes through this reaction. So we can, make an equation, although we're not really going to ever, I guess sometimes we'll make little calculations, but the change of enthalpy is how much enthalpy your products have minus the enthalpy of your reactants. And the units on enthalpy change are kilojoules per mole. So for example, this is the combustion of methane. And when you combust 1 mole of methane to produce carbon dioxide and water, the change in enthalpy is a negative 890 kilojoules per mole of methane. So 1 mole of methane combusted would produce negative 890 kilojoules per mole of enthalpy or energy. So think about that number. When you combust a mole of methane, you've got a negative enthalpy change. And according to this equation right here, the only way you're going to get a negative enthalpy change is if your reactants had more energy than your products did. So in this case, through the course of the reaction, your reactants had more energy than the products did. So energy was released by this system. That's what the negative means. And you know that's true because combustion gives off heat. It releases heat. The same would be true, or the opposite would be true for something that takes in energy. So if you have a positive delta H for your reaction, that means that that system is actually absorbing energy. And remember, when energy is either given off or absorbed, it's got to go somewhere. So for a negative delta H, for a system that's giving off or releasing energy, it's releasing energy from the system to the surroundings, right? So the surroundings are going to get hot. And when a system is absorbing energy, that energy is coming from the surroundings. So the surroundings are going to feel cold to you, or they're going to get cold. So just remember that. So you can actually write thermochemical equations or just chemical equations for thermochemical reactions. So that last reaction that we just looked at, where we showed the combustion of a mole of methane, we wrote the enthalpy change kind of separate from the equation, but you can actually write it into the equation as a reactant or a product. So as a product, what that means is that your system, as it undergoes its chemical change or its physical change, whichever the case may be, is releasing energy. So energy is a product. So you can just write the amount of energy as a product. Or you can write energy as a reactant if the system is absorbing the energy as opposed to giving it off. So when water molecules are broken down or decomposed into hydrogen and oxygen gas, they don't give off energy. They actually have to absorb energy to make that happen. So your enthalpy is written in as a reactant. So what about reversible reactions? Reactions that can go both ways. For example, you can have solid water melting, right, to produce liquid water, but you can go the other direction too. You can have liquid water hardening into solid water, so freezing. Well, the enthalpy change is going to be on different sides of the reaction depending on what's happening. So let's think about what happens when solid water melts. So does the solid water have to give up energy, or does it have to take in energy to be able to melt? So hopefully you realize that it actually has to take in energy to melt. So it takes in about 0.335 kilojoules per mole of water to melt. So our delta H would be a positive 0.335 kilojoules because we're adding the energy to our water to make it melt. But the reverse reaction where liquid water is turned into a solid is the opposite of this. You don't add energy to liquid water to make it freeze, you remove energy. So energy is actually lost from the system. So you would write energy or the enthalpy into the reaction as a product. Or if you were going to write it off to the side, you would say that you are removing 0.335 kilojoules per mole of energy to make 1 mole of liquid water freeze. So with a reversible reaction, your delta H value is the same, the magnitude is the same, but the sign is opposite when you reverse the reaction. All right, let's talk about heat exchanges between your system and your surroundings. So there are two possible situations. You have the situation where your system is releasing or giving off heat to the surroundings, or where the system is absorbing heat from the surroundings. So let's talk about this one, A, first. A is called an exothermic reaction. And the way I remember exo is exo sort of means exit. So heat is exiting the system to the surroundings. So what is that going to do to your delta H for your system? Well, your system is losing energy. So delta H should be a negative number. It's giving up energy. The other thing that we can say is that delta H is going to be a product for an exothermic reaction. And the reason why is because heat is being produced. Heat is going out of the reaction into the surrounding. It's being given off. And then we can also talk about what's going to happen to the temperature. So what kind of temperature change are we going to see? Now this is the tricky part. When you're measuring the temperature of a system, you're really not measuring the temperature of the system at all. You're actually measuring the temperature change in the surroundings. Your thermometer is part of the surroundings. So the change in temperature for an exothermic reaction is going to be a positive change. The temperature is going to go up because your surroundings are absorbing that heat and the temperature is going to go up. All right, let's talk about the other, let me first give you some examples of a exothermic reaction. So combustion is a exothermic reaction. The freezing of water is an exothermic reaction because it has to give up energy to freeze. And then, those little chemical hot packs that you crunch up and they make your hands warm, those are also an exothermic reaction. And an example of the equation for an exothermic reaction, in this case for what's going on in those hot packs contain powdered iron, and when you crunch the package, it releases that iron, so it's exposed to oxygen, and it produces iron oxide and 111 kilojoules of energy that you then can be used to warm your hand. All right, and a reaction where the surroundings are giving heat to the system, or the system is absorbing from the surroundings, these are called endothermic reactions. And the way I remember endothermic is endo means into. So heat is flowing into the system. So in this case, its delta H is going to be positive because it's taking in. So absorbing means positive. Delta H. Delta H is going to be a reactant because it's going to be taken in by your reactants to produce your products. Now this is the tricky one. When you're measuring the temperature change of an endothermic reaction, remember you're measuring the temperature of the surroundings. You are not measuring the temperature of what's going on in the system. It's what's happening to the surroundings. So of course, if you're measuring the temperature of the surroundings, you're going to have a decrease in temperature. So the temperature is going to go down because heat is being absorbed from the surroundings where the temperature is being taken. Examples of a endothermic reaction would be those cold packs, those chemical cold packs that you crush up and they get cold. Also the melting of water because you are having to input energy to get water to melt. And an example of a thermochemical equation for an endothermic reaction would be what's happening inside of those chemical cold packs. That is filled with ammonium nitrate, and when you crush it up, it dissolves it basically in water, and that absorbs 326 kilojoules. So water is a reactant, and energy is a reactant, and then that produces ammonia and nitrate ions. And in the process, your hands feel cold because energy is being sucked away from your hands. 326 kilojoules of energy per mole of NH4 is sucked from your hands into the NH4 as it dissolves. And finally, let's talk about how we can draw or interpret things called enthalpy and energy diagrams. So this is called an enthalpy diagram. So I have two of them here. One shows your reactants and your products. Notice the energy increases as you go up in this direction. So your reactants are releasing or losing energy to become your products. So an example of that would be the combustion of methane. Methane, when you burn methane, 890 kilojoules of energy is released. So your reactants are up here, your CH4 and your O2 are up here, and then your products have less energy than your reactants because this 890 kilojoules has been separated or released in the product. So this, of course, hopefully you realize, this is an exothermic reaction, or an enthalpy diagram for an exothermic reaction. And this enthalpy diagram shows your reactants, for example, your NH4NO3 in a cold pack, having to absorb energy in order to become NH4 in this case and NO3. So this is an enthalpy diagram for an endothermic reaction. It's showing energy being absorbed by your reactants to become your products. And another way you can write or express endo and exothermic reactions is something called an energy diagram. So up here we had our enthalpy diagrams, and an energy diagram is very, very similar. So for an exothermic reaction, really, the biggest difference is that you show this thing called activation energy. So again, your reactants, your CH4 and your O2 in our example for this reaction, which is exothermic, your reactants start up here and your products end up at a lower energy. So here's your CO2 and your H2O. And the overall enthalpy change right here is your 890 kilojoules that is lost as your reactants become your products. So that's from here to here. Then you have this thing called activation energy. So activation energy, we're going to talk about more in the next unit, but activation energy is really just that all chemical reactions actually require an input of energy to start, all of them. So you have to put in a little energy and then you get your product. So it's kind of like think about a roller coaster. For a roller coaster to happen, you have to give it a whole bunch of energy and then it can be a roller coaster. And the same is true for a chemical reaction. They all have a certain input of energy called activation energy. But what I want you to focus on is that your reactants are here, your products' energy are down here, which is a decrease or a loss of energy. So it's exothermic. An endothermic energy diagram, and you will be drawing these, so hopefully this makes sense. Your reactants start at a lower amount of energy than your products do. So your delta H here is going to be an increase. You're going from a lower amount of energy to a higher amount of energy. And so for this equation, it's your NH4NO3 down here, and then your NH4 plus and your NO3 minus as your products. Your delta H is a positive 326 kilojoules. So that's how much energy is gained or absorbed during the course of this reaction. And then your activation energy is a little tricky on this one. Activation energy is always where your reactants start up to the top of that curve. So this is your activation energy. They just drew the arrow here instead of here. All right, so that is the end of this. That's pretty much everything you're going to need to know about thermochemistry.